You know that fire burns. That's obvious. But what if I told you that ice can burn you too? And no, I don't mean that as some kind of metaphor. Today, we're diving into the really strange, really fascinating science behind the ice burn paradox.
I mean, it just doesn't make any sense, right? We use ice to cool things down, to soothe an injury, not to cause one. So how in the world can something freezing cold create the exact same feeling as something scorching hot? That is the central mystery we're about to unravel.
So, let's get one thing straight right away. When we say ice burn, we are being completely literal. It is a scientifically accurate term for real, physical damage to your tissue. The blistering, the cell death, the inflammation. It's shockingly similar to what happens when you touch a hot pan.
So to figure this out, we have to start with the physics of what's going on. It really all begins with what you could call a thermal theft, a great heat robbery that's happening on a microscopic level.
Okay, so think about it. Your skin is working 24/7 to stay at a nice, warm 37 degrees Celsius. That's 98.6 Fahrenheit. Ice, of course, is sitting at 0 degrees Celsius. The second you press them together, you create this huge temperature gap. And, well, nature just can't stand an imbalance like that. Heat starts pouring out of your warm skin into the cold ice at an unbelievable speed. So it's helpful to think of ice as more than just a passive block of cold. It's thermally aggressive. It actively and pretty relentlessly yanks thermal energy from anything warmer it touches, and it is incredibly good at its job.
In fact, it's 4 times better at it than you'd probably guess. Ice will pull 4 times more heat from your skin than cold water that's at the exact same temperature, 0 degrees. So why? Why is solid ice so much more dangerous than cold liquid? Well, the secret has this really cool name, the latent heat of fusion. The best way to think of it is like a cover charge at a club. Before the ice can even start to warm up, it first has to absorb a massive amount of energy just to pay that cover charge to melt into liquid. And where does all that energy come from? It's ripped directly from your skin cells. That's why your skin's temperature plummets so fast and so dangerously. All right, so we've covered the physics of this grand heat robbery. Now, let's zoom in and investigate the biological crime scene happening inside your body. What is all this rapid cooling actually doing to your cells? It's a truly devastating chain reaction. First, the fats in your cell membranes, which are normally soft and flexible, get stiff and brittle. Then, the water inside and around your cells starts to freeze, forming these sharp, microscopic ice crystals that literally poke holes in and shred those cells from the inside out. At the exact same time, your blood vessels clamp down, cutting off the supply of warm blood and oxygen. This starves the tissue, which only makes the damage worse. So, when you put it all together, what we call an ice burn is, in medical terms, just a form of localized frostbite. It's the exact same destructive freezing process, just happening on a smaller, more concentrated spot. And this damage happens on a spectrum, you know? It can start with something called frostnip, which is just on the surface and totally reversible. But if you're exposed for longer, it gets worse, moving to partial thickness frostbite. That's where you get blisters and inflammation. This is where most ice burns land. And at its absolute worst, you get deep frostbite, which is just severe tissue death. Okay, so we get the physical damage now. The cells are freezing and dying. But that still doesn't explain the feeling. Why does it feel like a burn? Well, this part of the puzzle involves a kind of strange betrayal by your own nervous system. The answer lies with these things called nociceptors. Think of them as specialized pain receptors in your skin. But here is the absolute key. They aren't just heat detectors. They're danger detectors. They're specifically tuned to sound an alarm in response to any extreme temperature, whether it's super hot or super cold. And this is the moment it all clicks. It doesn't matter if you touch a hot stove or you press ice against your skin for too long. The very same nociceptors start firing. They send nearly identical electrical signals racing up to your brain. And your brain, getting this urgent danger message, has pretty much one all-purpose interpretation for it: burn. You know, from an evolutionary standpoint, this makes total sense. Your body's #1 priority isn't to give you a detailed weather report, it's to make you yank your hand away from whatever is causing damage, and to do it now. That burning sensation is just a simple, brutally effective universal alarm to get you to move and protect your tissue, no matter what the source of the danger is. So let's bring all this science back into the real world. Now that we understand what's happening under the hood, we can see why respecting the cold is every bit as important as respecting heat. And these burns happen in really common situations.
The number one cause, by far, is just slapping an ice pack directly on your skin without a towel in between. Another is, holding on to ice for too long, maybe for a silly bet or a challenge. Even just compressing ice against your body can do it, because that cuts off circulation and makes the tissue freeze even faster.
And look, regular water ice is dangerous enough, but the danger just skyrockets with colder substances. You've got dry ice, which is a mind-numbing -78.5 Celsius that can cause a serious burn in just seconds. And then you have liquid nitrogen. We're talking almost -200 Celsius. At that temperature, the damage is practically instantaneous.
And this is maybe the most shocking part of all. If you look at the cellular destruction from something like liquid nitrogen, the dead tissue, the deep permanent damage, it is virtually indistinguishable from a severe third-degree burn caused by actual fire. The two opposite extremes of temperature meet at the exact same terrible destination: total tissue destruction.
So in the end, the paradox is solved. An ice burn feels like a fire burn because, frankly, your brain just doesn't care about the difference. To your nerves and your brain, extreme thermal danger is just that, danger. And that burning feeling, that's its one and only alarm bell, a desperate signal to save your cells from being destroyed, whether it's by fire or by ice.